Each object type in C++ has a property called alignment requirement. The alignment, similarly to the type size, is implementation dependent. Here you can see some of the fundamental data types and their corresponding alignment requirements that are most common. The alignment is the same for unsigned types. For example, an int or unsigned int has the size of 4 bytes, and their alignment is also 4 bytes. For simplicity, I'm going to concentrate only on 64-bit applications, so pointers in further examples are going to be 8 bytes with 8-byte alignment. The alignment tells us on which address boundary the given data type should be placed in memory. Let's take a look at this simple memory grid. Each cell represents 1 byte. In case of an int with 4 bytes alignment, the beginning address has to be divisible by 4 in order for an object of type int to be considered aligned. Otherwise, the object would be unaligned. For double with 8-byte alignment, the object has to be on the address that is divisible by 8. The reason for the alignment is that on different CPU architectures, unaligned access can come with different performance issues, depending on the implementation. Even though modern x64 CPUs do a great job with handling unaligned memory, there are situations where unaligned data is going to create some issues. One example is data that resides on a cache line boundary. It's not only going to take more cycles to access such data, but loading this data into the cache can trash your existing cache content by invalidating 2 cache lines instead of 1. The alignment is also important when using SIMD or atomic instructions, which I'm not going to cover in this video. Intel advises to use properly aligned data in their programming manual. The same goes for AMD. C++, on the other hand, requires from us to use a proper alignment. Dereferencing a pointer with an unaligned object gives undefined behavior. In this simple example, we have a long object with 8-byte alignment. We get the address of that object and shift it by 1 byte, storing it inside int pointer. In the return statement, we are dereferencing this pointer. Now, we can compile this simple program using Clang with undefined behavior sanitizer enabled. When we run this program, the undefined behavior sanitizer detects that the int pointer we are trying to dereference has the unaligned object. Now let's talk about alignment requirements for structures. When creating a structure's memory layout, the compiler is going to place each member in the order they are declared in the program. First, short with 2-byte alignment, it can be placed at the address 0. Next, char with 1-byte alignment can be placed at the next address 2. Pointer with 8-byte alignment can be placed in the first row because none of these addresses are satisfying pointer's alignment. The first valid address is address 8. The last member, float, with 4-byte alignment can be placed at the next address, address 16. As you can see, the compiler inserts additional padding to satisfy structure's alignment constraints. The structure has also the alignment. The alignment for the structure, by default, is the largest alignment of all structure's members. In this example, the alignment is going to be 8 bytes, since the pointer, member C, has the largest alignment. At the end of the structure, the compiler will insert additional padding to make it divisible by the alignment. The padding at the end is added to make sure that when the structure is used as a type of an array, each entry is going to be properly aligned along with its members. Now you know what is data alignment in C++ and why it is important. Hope you guys learned something new and interesting today. If you have any comments or questions related to this topic, don't hesitate to ask in the comment section.